Hello everyone, my name is Quan-Zhi Zhang. I am from China. Currently, I am a Marie Curie Fellow at the University of Antwerp in the research group of plasma. My supervisor is Professor Anime Bogas. My current research focuses on cryogenic plasma etching for porous material. It's really a great honor to obtain this prestigious Marie Curie Fellowship, which allows me to carry out research in Europe. I definitely believe that the knowledge, experience, and other complementary skills like business skill, management skill, and even language skill, which I will learn from this project, will advance my future career. After completion of this project, I plan to build up a career in microelectronics industry in Europe. Next, I will introduce my work briefly. Hope you can enjoy it.
Now let us see how computers help in making faster and more powerful computers. Nowadays, electronic devices like computers and cell phones are becoming very important in our modern life. However, the most important part in a computer is the microchip. We always try to develop more powerful microchips for powerful computers. This is an image of microchip. It has the size of square centimeter, but it contains at the moment billions of transistors, so it's not easy to fabricate. To produce microchip, we need to start from a circular silicon substrate, which we call a wafer. After many steps of processing for weeks by repeating etching, deposition, and mapping, we can get the finished wafer, which is then cut into computer chips. During this processing, we will use plasma technology. So what is plasma? Plasma is the ionized gas. It's the fourth state of matter. Take ice as example. When ice is sufficiently heated, it melts to form water. When further heat is up, water can evaporate from a liquid to a gas. When the heat is sufficiently strong, the molecule in gas will dissociate into charged species, which is plasma. Basically, we do the plasma simulation in our group. We calculate to see how the plasma behave in the plasma reactor. On the left of this page is plasma reactor. The bottom is the substrate for putting the silicon wafer. On the right is the movie for plasma etching. Reactive species can be generated in the plasma and then accelerated to the substrate and remove pieces of materials. This is another example for etching from simulations. It shows two processing with removing materials with different gas mixture. The left etching has undercutting, which is not good, but for the right one, the oxygen can provide sidewall protection and contribute very good etching profile. As you can see, simulations can always help predict the optimal conditions for fabrication to get the better results. Thus, microchip development and evolution can be greatly improved and speeded up by computational investigations. Experimental validation for my simulation will be conducted in the group of Grammy in France. Thank you.
Hello everyone, I'm Yanping Zhu, come from China. I'm a postdoctoral student sponsored by the Marie Curie Fellowship. Right now I work in Organic Synthesis Group at Antwerp University of Belgium. My supervisor is Professor Bert Maas. The Marie Curie Fellowship is a very prestigious fellowship in European Union. I really appreciate it gives me the opportunity to carry out research in Europe for 2 years. So what can I learn and what can I get from the Marie Curie Fellowship? The prestigious grant allowed me to gain good experience abroad and learn new techniques and will add valuable publications to my CV. It also gives me more chance to attend the international conference, communicate with very famous professor. During the process of the fellowship, I had got some training. For example, professional knowledge, chemistry safety education, managing skill, communication skill, and language ability. All of these benefits are useful and helpful for my future academic career. After I finish the project, I will return to China and establish my own research. Next, I will give a brief introduction for my work. Wish you enjoy it. My research topic for the Marie Curie Fellowship is sustainable amide synthesis. As we know, the amide functionality is one of the most important units in organic chemistry. It is also widely present in features polymers, natural products, top-selling drugs, and agric chemicals. It is present in more than 25 of all launched pharmaceuticals and 2/3 of the drug candidates. Up to now, there are many methods for amide synthesis. The procedures starting from carbonic acid and amines are still the most interesting due to the widespread availability of these building blocks. But they also have some limitations. For example, simple scope using expensive carbonyl reagents and optimization for chiral amino acids. As an alternative approach, amine activation has been developed. Its main advantage is that it can avoid the optimization for alpha chiral amino acid. But up to now, only a few procedures has been developed based on this approach. Based on our previous result, we developed isocylurea as a new class of activated amines suitable for amide synthesis. These protocols use the aryl catalyst under amide conditions, reaction conditions, and is especially suitable for the synthesis of very challenging amides. It can efficiently avoid the optimization for alpha chiral amino acid. Interestingly, the diphenia sulfide byproduct can be isolated in very good yield. It can also be transformed into ephenia benzoyl sulfonate reagent. It is very sustainable. Now I give some examples for the sustainable chemistry that I learned from this project. Chromatography is the most common method used for purification or desired product. Before, I only used the glass chromatography column. It needs a lot of steps for purification a compound, such as layer of sand, adding silica gel, loading sample, adding mobile phase, elution, throw away the silica waste and the solution. So the process is very complex, where waste master time, solvent and silica. From the point of sustainable chemistry, it is not sustainable anymore. In my project, I learned to use the atom flash chromatography machine. We call it BioTouch. It integrates all functions in one machine. It will save much time, a lot of solvent and silica. Next, I will show some information about the BioTouch and the solvent recycle system. So this is the atom flash chromatography machine. With this machine, it can save much time and a lot of solvent and silica gel. Because you use this system, you don't need to waste the silica gel and the solvent. The solvent will come to the waste container. It can be recycled for use again. Next, I will give some information for the solvent recycle system. So this is the solvent recycle system. With this system, you can distill your waste solvent from chromatography. Then, based on different boiling point, you can collect your pure solvent.
Hello everyone, my name is Wei-Zong Wang from China. Now, I'm working at the Department of Chemistry in the University of Antwerp, supported by European Marie Curie Individual Fellowship. In 2007 to 2013, I was involved in a dual doctorate degree program between China and UK. With this program, I have an opportunity to do the research in UK. This experience makes me fully believe that an international environment is extremely important for a young research scientist's career development. This is the reason why I got in touch with my host professor, Professor Anime Burgers, and decided to apply for this European Marie Curie Individual Fellowship. My project, supported by this grant, is about the understanding of greenhouse gases conversion into value-added chemical products by gliding arc plasma. I fully and deeply believe that this experience through this grant will build up a solid foundation for my lifelong research career.